Good morning. Welcome to NGSS Physics. We are going to be going over lesson 4.4, which is on work. You can find this in your CK12 online physics book, sections 4.1 and 4.2. So far, before we get started, go ahead and grab your calculator, grab something to write with, because there are going to be a few calculations to work through today. Okay, so far we've learned how to calculate potential energy and kinetic energy, and we didn't say very much about them other than one was the energy of motion, the other is the stored energy. What exactly does that energy do for us? Well, it gives us the capacity to do work. And if you think about work and energy, it makes a lot of sense since when you do a lot of work, you get low on energy, or if you got a lot of energy, you could do a lot of work. We can make the definition of energy a little bit more precise if we specify exactly what we mean by work. So let's take a look at that. Um, in physics, we like to define work as getting something done. So basically applying a force that actually does something. And forces, remember, change motion. And so in this case, we're going to have that force push an object or move an object a certain distance. And that is going to be what we call work. So we can write it in a formula that looks something like this, where W will be work, F will be the force that's applied, and D will be how far that object moved. So you have to actually have some motion or movement to get some work done. If you don't move the object, then you haven't done any work, even if you applied a big force. Speaking of forces, we know that objects usually have more than one force acting on them at all times. The only force that we're concerned with in the work formula is the force that actually changes or moves the object. So it's the force that acts in the direction of motion, not necessarily work itself is not necessarily a vector, but force is a vector. So negating all the other forces and just using that force. Well, that leaves us to, what are the units for work? Well, if energy gives us the capacity to do work, and when you're working, you're using energy, then it makes a lot of sense that the units for work are going to be similar to the units for energy. Let's see how that works. Remember, force is actually mass times acceleration. That's the formula we use to get there. And the mass is measured in kilograms, and the acceleration is measured in meters per second squared. And we said that kilograms meters per second squared, we gave a new name called the Newton. Okay, so that is what force is. And then work is actually force times distance. What would the units be here? Here are the units for force, kilograms meters per second squared. And then we have the meters, which is the distance. Put them all together and you get kilograms meters squared second squared. Or you could just say Newton meters. If you recall from calculating potential energy and kinetic energy, kilograms meters squared second squared basically was the joule. So a Newton meter, kilogram meter squared second squared, or a joule, those are all the same thing. And so work, which is force times distance, is really MAD, and it has the same exact energy, units as energy, joules. Here we go. MA is what force is, and here's my D, my distance. Doing work makes you mad. Ha, ha, ha. Let's see. Remember that formula for potential energy, which is mass times acceleration to the gravity due to the height? Well, remember the height is like a distance. G is the acceleration due to gravity. And so we got mass acceleration and distance, mass acceleration. It's really the same exact formula. The potential energy formula, because it's against gravity, basically goes up and down, using gravitational pull, whereas the work formula can go in any direction. All right, let's take a look at a sample problem. Dancer lifts a 400 Newton ballerina 1.4 meters overhead. How much work is done? Remember, work is force times distance. Here's a distance. Here's a force. Plug them in, and you get 560 joules. Check your answer. Here's another question. What work is done? 200 Newton box is pushed with 160 Newtons across a 5-meter floor. Well, work again is force times distance. Here is a force, here is a force, here's a distance. Which force do we use? We only use the force associated with that change in um, position. So it's being pushed across the floor with 160 newtons. It doesn't really matter that it's a 200 Newton box. So we plug those numbers in, and what do we get? 800 joules. A superhero pushes a grocery cart 7 meters to the checkout line. If you did that much work, how much force do you use? Well, here is my formula. Okay, we're looking for F, so I'm going to divide out by D on each side. Cancels out on this side, and force is equal to the work divided by the distance. Just like that, plug those numbers in, I get 500 newtons. Bart has a weight of 120 newtons. He climbs a ladder and he attempts to escape. Okay, remember, work is equal to the force times the distance. In this case, the distance is the height. Okay, so I divide out by F on each side, and I get the distance that he climbs is work divided by force. Plug those numbers in, 10 meters. All right, remember, kinetic energy is the energy of motion, and everything that is in motion is basically moving things and carrying that energy around. We had this formula that got there, and the units were also joules. So energy in motion. Kinetic energy formula works very well. Note that the V to the second power, it's dependent on this. Why? Okay. Well, if you have things in motion, it's a lot more energy the faster it goes. A car at 60 is 4 times more dangerous than a car at 30. Hurricane force winds at 100 miles per hour are much more destructive, 4 times as destructive as hurricane winds at 50 miles per hour. A bullet shot through a gun is much more destructive than if you just threw it across the room. Even if you could throw it as fast as you could, still wouldn't do that much damage. Okay. Remember, for kinetic energy, the units are kilograms meters squared second squared, which is also the joule. And then we had gravitational potential energy. Okay. The force of gravity is mass times g, which is the acceleration due to gravity. This is very similar to just mass times a, which is any acceleration. We're just being more specific when we're talking about gravitational potential energy. So that, like I said on the previous slide, these two formulas are actually exactly alike. Mass times acceleration times distance. It's just that when it's against gravity, it's a height, and we have an acceleration already known. Again, the units are kilograms meters squared second squared. So when you do work against gravity, you can actually use the PE formula to calculate how much work that you've done, because you're actually using the same formula. Lifting a height against gravitational force requires some work. The change in energy, you can see, is equal to the work, which is the force times the height. The force in this case is mg, okay, and the acceleration is 9.8 instead of just any acceleration, and the distance is the height. Let's take a look at ramps. Why do ramps work? Well, you take the same amount of work done in 2 different ways. Okay, either way, you're going to get a large force being applied over a small distance. Like right here, I got a small distance that it's being moved, and it takes a big force to do it. Or I can do a small force over a much larger distance, like pushing it up the ramp here. I'm going a lot further, but it doesn't take as much force to get there. Either way, I'm doing the same exact amount of work. So that's why ramps work very well. It's a very simple machine. Let's take a look at some more sample problems. Remember, PE and work are the same. MGH is MAD. And so either way that you look at this, um, you've done the same amount of work. Okay, 2 ski lifts were built at a resort. A shorter lift with a steep angle and a longer lift with a gradual angle. Which lift results in more gravitational potential energy? Well, let's take a look. Potential energy is, if you remember what your formula for potential energy is, it is PE is equal to mgh. Well, if the ski lifts have the same mass, the same gravitational pull from the earth, and they go to the same height, then I would say that they have the same exact gravitational potential energy. Number two, which lift does more work, taking the passengers to the top? Let's take a look at the formula there. Work is equal to force times the distance. And remember, the force is the mass times the acceleration. Okay? The distance. If they have the same mass and they were taking a different force to get there because one of them's got a higher, steeper angle, then I would say that the work, because the PE is the same, the work was also the same. It's kind of like our ramp example. Okay, different amounts of force to get it up there, but still the same amount of work. Okay. Both of them were the same. Okay, sample questions. Calculate the work if 17 newtons of force pushes the car 0.52 meters. Use the work formula. Work is equal to force times distance. Here's my force, here's my distance. Plug it in and see what answer that you get. Calculate the force if a certain amount of joules of work are done to move something. Well, if the work formula is force times distance, I know that the force is going to be equal to the work divided by the distance. Here is my work, here is my distance. Plug those numbers in and see what you get. The distance, well, if work is equal to force times the distance is going to be equal to the work divided by the force. We're just dividing out by F on each side. Here is my work. Here is my force. Yeah, force is in newtons. Plug those numbers in and see if you get the correct answers. Now check them. Here they are. Alrighty. Work is defined as a force causing the movement or the displacement of an object. Work can be quantified with a formula. W is equal to FD. Really, work is energy. And so work has the same exact units as energy, the joule. And this ends ends our work for today. I'll see you back in the main classroom. Thanks for listening.